Assalamualaikum and salam sejahtera. The third learning unit would be lipid. So these are the learning objectives for this learning unit. You should be able to define lipid and explaining different classes of lipid. Secondly, explaining what are the function of fat in food. Thirdly, summarizing auto-oxidation process in food. And lastly, explaining the chemistry of frying. So what are lipids? Lipids are a broad group of chemically diverse compounds which are soluble in organic solvent. So they are not soluble in water but soluble in organic solvent. And they are referred to as fat or oil. Fat referring to the solid form of lipid and oil referring to the liquid form of lipid. Okay, so this solid and liquid is based on their physical state. So the major component of lipid are fatty acid. Fatty acid are the compound that contain aliphatic chain with a carboxylic acid group. So the majority of fatty acids of lipid would be in the range of 14 to 24 number of carbons. And fatty acids are classified either as saturated or unsaturated. Unsaturated means it has double bond. So these are the general lipid molecule. Structure consists of a head part, glycerol, which are hydrophilic in character, and then the tail part, which are hydrophobic in character. And this tail part goes up to 3 fatty acids. So this is referring to one fatty acid, another tail refers to another fatty acid, the third one will refer to another fatty acid. So fatty acid can be described by systematic, common and also abbreviated names. So first of all, we will look at the nomenclature of saturated fatty acid. Now, naming of saturated fatty acid would be based on the number of carbon in the acid. So if there are 10 number of carbon, the name of acid would be decane. Note that it ends with letter E due to the number of 10 carbon, but because this is acid, we replace the NE with OIC or wick, so it becomes decanoic acid. So this is very simple, basic that you have learned before. Okay, so this would be the numerical abbreviation for fatty acid. We use numerical system. For example, hexadecanoic. So hexadecanoic means 16 number of carbon. So the commercial name for this kind of acid is palmitic acid. So palmitic acid will have no double bond. So the numerical abbreviation or the numerical system for this hexadecanoic acid will be 16 semicolon 0. So 0 means indicating no double bond, 16 indicating number of carbon. Next, we will look at the nomenclature for unsaturated fatty acid, means it has double bond. So due to the presence of this double bond, the anoic of the naming would become anoic. Okay, from anoic become anoic. So the numerical will be the same. Okay, as saturated acid means instead of 0 for the second number after the semicolon, you have number, okay, indicating the number of double bond. For example, here octadecadienoic acid. Okay, note that enoic here. So it has 18 carbon, okay, with 2 double bond present. Now, based on this nomenclature, you don't know the position of the double bond, but you know the number of the double bond. So therefore, to know the position of the double bond, we use the delta system. Okay, indicate by this symbol here, triangle symbol. For example, here, oleic acid, which is the common name or the commercial name, for the systematic name is 9-octadecenoic acid. So 9 is the position of the double bond from the carboxylic end, or carbon 9. Okay, so this is carbon 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and in the numerical abbreviation, we write it as 18 colon 1 delta 9. So this will indicate there are 18 carbon with the presence of one double bond, okay, at position of carbon 9. Okay, delta 9. So alternative to the numbering system, we use omega system. Omega system, on the other hand, indicate the position of the double bond from the methyl end. So in the delta system, it's is counted from the carboxyl end, whereas omega system we count from the methyl end. Now, the omega system is useful in the context of human diet. Okay, so we use omega system because it is classify the position of the double bond closest to the omega carbon. So omega carbon is counted from the methyl end. Okay, so this is omega carbon. Okay, then the subsequent is omega 1, omega 2, okay, carbon omega 1, carbon omega 2, and so on. So this table shows the systematic name for different type of fatty acid, their common name or the commercial name, the formula, the shorthand description, or the abbreviated name. Now the previous table shows the saturated fatty acid, okay, without presence of double bond. So this table here shows unsaturated fatty acid, means there are presence of double bond. Okay, so again, this first column shows the systematic name, followed by the common name, the formula, and the abbreviated numbering. So note that this abbreviated numbering uses the omega system. So means it is in the context of human diet. Okay, so the omega system is used in the context of human diet, where the classification of the position of the double bond is the one closest to the omega carbon, so means from the methyl end. Okay, for example here, okay, so this is the methyl end, so this is carbon omega, okay, omega carbon. Okay, then the subsequent is omega 1, okay, omega 2, omega 3, 4, 5, 6, 7, and so on. Okay, so if you look at linoleic, linolenic, and also arachidonic, they are classified as omega 6 due to the formula of the acid are the same. Okay, so if you look here is CH3, CH2, okay, 4, and followed by CH, double bond CH, CH2. Okay, same goes to linolenic also, CH3, CH2, 4, CH double bond CH, CH2. Okay, so the pattern are the same. Okay, so omega 6 means here, okay, the position of the double bond is at omega 6, okay, the first double bond. Whereas for linolenic, EPA and also DHA, okay, the first double bond from carbon omega is at omega 3. Okay, so CH3, CH2, CH double bond CH. Okay, also similar here, CH3, CH2, CH double bond CH. Okay, CH3, CH2, CH double bond CH. Okay, so when this number here, okay, after the colon indicates the number of double bond. Okay, so like here, okay, the following double bond is of course at omega 9. Okay, here the first is at omega 6, omega 3, second is omega 6, the third one is omega 9. Okay, and that's how you see the position of double bond. Okay, next we move on to the classification or division between saturated and unsaturated fat. This is useful in food technology in terms of their physical properties, because saturated fatty acid would have much higher melting point compared to unsaturated ones if we compare in terms of their carbon number. Okay, so the ratio of the saturated fatty acid to unsaturated significantly will affect the physical properties of a fat or oil. Now, the scientific name for ester of glycerol attached with fatty acid is named acyl glycerols. So over 99% of fatty acids that are found in plant and animals are in terms of esterified version to glycerol. And these acyl glycerols can exist as mono, di, and also triesters. And they are named monoacylglycerols, diacylglycerols, and also triacylglycerols respectively. However, the more common names for these compounds are monoglycerides, diglycerides, and also triglycerides. So if you come across monoacylglycerol, it's the same as monoglycerides. Now the glycerol is attached to the fatty acid. So if the fatty acid is only one, it's called monoglyceride. So if the glycerol is attached to two fatty acid, then they are named as diglyceride. And if the glycerol is attached to three fatty acids, then it is called triglyceride. Of all these three, the triacylglycerol or triglycerides are the most common, okay, in food. And the usage of these glycerols are as food additives, okay, for example, as emulsifier, okay, to mix immiscible oil and water. Okay, this is how triglycerides are formed. So this is glycerol, okay, and there are three fatty acids here. So one glycerol attached to three fatty acids through condensation reaction will form triglyceride and also three water molecules. So if one glycerol attached to one fatty acid, then monoglyceride will form. And if glycerol react with two fatty acids through condensation reaction, then diglycerides will form. Okay, next we move on to lipids. The components of lipids are majority is contributed by triglycerides, which is 95%. The second component of lipid is phospholipid. For example, is lecithin, which is found from soya. Third is sphingolipids. For example, sphingomyelin, ceramide, cerebrocytes, gangliosides, which are commonly found in nervous system. Next is sterol, for example, is cholesterol, and last is waxes. Okay, first we will look at phospholipids. So phospholipids are the modification of triacylglycerols where the non-lipid component is phosphate groups, okay, like in LU2 we have phosphoprotein, so it has phosphate group, okay, in the protein component. Similarly, phospholipid has phosphate in the lipid, okay, so it's the non-lipid component is phosphate. The advantage of phospholipids, it can prevent crystallization at ambient temperature due to its polar in characteristic. Okay, so when it's polar, it will prevent crystallization, especially when applied to food products. So all fat and oil containing food will have phospholipid in them, and the lowest amount of phospholipid are present in pure animal fats such as lard and beef tallow. So high phospholipid are found in plant origin. So in some vegetable oil, for example, cottonseed, corn, soybean oil, the phospholipid present at rather low percentage, which is in the range of 2 to 3. In fish, crustacea, mollusk, those with shell will have about 0.7% phospholipid in the muscle tissue. So most phospholipid are obtained, high phospholipid are obtained from soybean oil, and they are used as emulsifier in certain foods, for example chocolate, which enable mixing of immiscible oil and water component, so it acts as emulsifier. So soybean phospholipid contain about 35% lecithin, and the rest are cephalin. And the lecithin are the one that has both hydrophilic and hydrophobic character. So if you look at this chocolate packaging, okay, you will see one of the ingredient is lecithin, okay, normally from soybean origin, which are used to act as emulsifier to enable oil and water to mix. Okay, so you can see here, okay, soy lecithin. Okay, another packaging of chocolate. Okay, you can see here soy lecithin. Okay, this slide shows the structure of major phospholipid found in plants. Okay, so lecithin and cephalin. Lecithin, which is actually the chemical name is phosphatidylcholine, and for cephalin the chemical name is phosphatidylethanol-amine. Besides lecithin and cephalin, there are also phosphatidylserine and phosphoinositides content as well. So the next next component of lipid is sterol. Sterol are the derivatives of steroids, and these are example of non-polar lipids. Okay, so if phospholipid is polar lipid, sterol is non-polar lipid, and they have 3 6 carbon ring and 5 carbon ring attached to an aliphatic chain. So this is the general structure of sterol. You see 6 carbon ring with 5 carbon ring, and they are attached to aliphatic chain. So sterol, of course, will have OH group attached to carbon 3 of a ring, and if they are found in plant, it is called phytosterol, and if the sterol are found from animal origin, so we call them zoosterol. So easy to remember. Okay, zoo normally associate with animal. So the animal lipids, the major sterols are cholesterol. Okay, in plant lipid, the major sterol are beta sitosterol and stigmasterol. Dietary phytosterol will decrease the cholesterol absorption in our intestine. Okay, and therefore these phytosterol are added to food to reduce blood cholesterol level. So normally cholesterol is associated with as bad lipid, okay, compared to plant origin. So that's why dietary phytosterol is added instead, in order to decrease the cholesterol absorption. So this is the general structure of sterol. So you see there are 3 6 carbon ring here attached to 5 carbon ring, and they are attached to a aliphatic chain. So this is steroid and this is cholesterol. These are the plant sterol. Okay, stigmasterol, beta sitosterol, camptosterol, and brassicasterol. The next component of lipid is wax, and they are classified according to the origin. like sterile also. From animal, it's called beeswax. From plant origin, it's called cannabis wax. And if from mineral, it's called petroleum wax. Wax are found on the surface of plant and also animal tissue in order to repel water and also prevent the loss of water, okay, from the structure, from the tissue structure. And wax are commonly added to the surface of fruits in order to slow down the dehydration of the fruits, especially during storage for export purposes. So therefore the fruit will last longer. Okay, next we'll look at physical properties of fatty acids, saturated versus unsaturated. So here we look at saturated stearic acid having 18 carbon in its chain. The melting point for this stearic acid is 73 degrees Celsius. However, if we compare with another fatty acid, specifically unsaturated fatty acid, in this case here is oleic acid, having the same number of carbon, which is also 18, but with the presence of one double bond, the melting point decreases drastically to only 5.5 degrees Celsius. So here we can conclude that if the double bond increase, the melting point will decrease. So as there are more double bond, the melting point become lower. Okay, if we want to compare between saturated acid, fatty acid, the longer the chain, the higher the melting point would be. So here is another two unsaturated fatty acid. So here linoleic acid have 2 double bond, linolenic acid have 3 double bond. Look at the melting point value. Okay, as the double bond increase in number, the melting point will also on the other hand will decrease. So here we'll have negative 13 degrees Celsius. 3 double bond will reduce further to negative 24 degrees Celsius. And that is why if there are more double bond present in fatty acid, it is reducing in terms of its oxidative and thermal stability. So it becomes more unstable. Okay, as the double bond increases, and that is why fatty acid with high number of double bond is susceptible to lipid oxidation due to its low stability towards oxygen and also heat. So this is comparison of the monosaccharide, linoleic, linolenic, and saturated fatty acid content in different origin. Okay, so if you see here, high oleic sunflower will have highest percentage content of monosaccharide compared to saturated fatty acid. Okay, on the other hand, coconut will have the highest content of saturated fatty acid compared to monosaturated, and also unsaturated linolenic and linolenic. Okay, so coconut oil therefore is oxidatively and thermally stable compared to safflower, which has high percentage of linolenic and linoleic double bond unsaturated fatty acid. Okay, so high percentage of double bond fatty acid will susceptible to lipid oxidation and also thermal degradation. So next we'll look at the function of fat in food nutritional role. Okay, why fat is important in our diet. Okay, so if you want to go for diet, you cannot eliminate fat totally from your diet intake, so you need also fat in your diet, but in control amount. Why is that so? Because it's the only source of essential fatty acid. Similar like protein, you need essential fatty acid which cannot be produced by your body, so you can only get it from your diet. Okay, the food you take. So example of essential fatty acids are linoleic and linolenic. Another purpose of fat in our diet is as carrier for fat soluble vitamin. So vitamin A, D, E and K also important for your body. So in order for these A, D, E, K vitamins to be absorbed by your body, you need the carrier for it, and which is fat. So without fat, how your body can absorb these 4 vitamins? So you need fat. And of course, the third reason of fat is source of energy. So it supply 9 kilocalorie for every gram of food versus only about half 4 kilocalorie per gram if you take carbohydrate or protein. Next we will look at the functions of fat in food in terms of its appearance and also texture. Now first we look at the appearance. So solid fat will look opaque compared to liquid oil, which is clear. This is because light passing through solid fat is scattered by the fat crystal present in the solid fat, which make them look opaque. Whole milk, on the other hand, which has 4% of fat content, will appear whiter compared to skim milk, which contain only less than 0.1% fat, due to the fat globule in the whole milk that scatter light strongly, unlike skim milk, which only have casein micelle, scatter light more weakly. In terms of texture, shortening are fats that are used to provide functional properties, especially for baked products, for example cakes, breads, pastry, and example of functional properties given by shortening, for example are tenderness, texture, mouthfeel, incorporation of air, so that it look more fluffy, okay, and at the same time extending the shelf life of the baked products. Shortening also able to prevent interaction between protein or starch molecule, um, which serve to tenderize the product. And shortening also have the ability to form three-dimension fat crystal network, which provide the textural characteristic of the food products. Next, we look at flavor function. The even carbon numbered and short chain fatty acid in the range of carbon 14 to carbon 12 will impart cheese flavor to food product. And hydrolysis of hydroxy fatty acid, which will form lactone, provide coconut and peach like flavor to food product, and it's not actually directly from coconut or peach. Next function is mouthfeel. Of course, liquid oil will give oily mouthfeel when eaten, and fat crystal will give grainy mouthfeel if they are large, but if they are small in size, it is more smooth in terms of texture. The melting of fat crystal in the mouth will cause a cooling sensation to the people eating the food product. Okay, next we move on to auto-oxidation. So what is auto-oxidation? It's actually undesirable chemical reaction which involve oxygen that will degrade the quality of an oil. The undesirable is caused by the formation of secondary products. So before formation of secondary products, it started off with formation of primary products, which followed by its decomposition to secondary product, and then this secondary product will leads to formation of tertiary product. Okay, the secondary products are the one that is responsible for the undesirable food, undesirable reaction to food, which is termed rancidity, which is actually referring to oxidative deterioration. Now, the auto-oxidation are divided into three parts, which are initiation, propagation, and termination. So, what leads to auto-oxidation or lipid oxidation to lipid-containing food? It's the major reactant are the unsaturated fatty acid. Remember, I have covered the physical properties between saturated and unsaturated. So when there are more double bond presence, it becomes more unstable to oxidation or heat. Okay, so the more double bonds that are present, the susceptible it is to lipid oxidation. So if we see in this table here, okay, the energy needed to remove hydrogen, okay, in saturated compared to unsaturated um, with high number of double bond is higher. Okay, for example here, it needed 100 kilocalorie for every mole to remove hydrogen. Okay, this hydrogen here. Whereas in unsaturated fatty acid having two double bond here, the removal of this hydrogen is easier. Okay, it need less energy, which is only 65 kilocalorie per mole. So let us look at the mechanism for lipid oxidation or autoxidation. So it will initiate when the hydrogen atom at the methylene group in double bond of unsaturated fatty acid is removed. Okay, so you have the unsaturated fatty acid here. Okay, the hydrogen is removed. Okay, at the methylene group. Okay, in the double bond, it will form alkyl radical. Okay, alkyl radical here as well as hydrogen radical. Now, how does this formation of radical initiate? It's initiated by enzyme called lipoxygenase. Okay, so in order to prevent the initiation of lipid oxidation, then we have to remove this enzyme. So how to remove this? By short heating. Okay, because enzymes are very sensitive to heat, so we can inactivate this enzyme by heating. Besides enzyme, another factor that can initiate lipid oxidation is the presence of metal ion. For example, iron, cobalt, copper. And these metal ions are found naturally in food, which are actually from metal equipment used during the food processing. So to prevent the initiation of lipid oxidation by metal ion, we can chelate this metal ion using chelating agent such as EDTA or citric acid. Now, once the lipid oxidation has been initiated, it will propagate. Okay, the free radical that has been formed during the initiation process will combine with oxygen from the surrounding to form a peroxy free radical, and these peroxy free radical can abstract hydrogen from another unsaturated molecule, which would also yield a peroxide and also a new radical. Okay, and this new radical will combine with oxygen to form another peroxy free radical, and this reaction will be repeated up to several thousand times. Okay, so we consider this as chain reaction. Okay, and this chain reaction will only terminate when they meet with another free radical. Okay, so this is the mechanism of propagation. During the initiation process, free radical is formed, and that free radical form will combine with oxygen from the surrounding, forming a peroxy free radical, and this peroxy free radical will abstract hydrogen from another unsaturated fatty acid to form peroxide and a new free radical, and this will continue as chain reaction, forming another free radical and so on. So the hydroperoxide that is formed in the propagation step just now are named as primary oxidation product. And these primary oxidation products are unstable, so they decompose into secondary oxidation product. Secondary oxidation products include carbonyl, aldehyde, and which are responsible for the rancidity of food. So the secondary oxidation product, one of it is aldehyde, are themselves oxidized and forming fatty acid, and these fatty acids are considered as the tertiary oxidation products. The propagation will only terminate once the free radical meets with one another. For example, here the alkyl radical meet with another alkyl radical, or the alkyl radical meet with peroxy free radical, or between the peroxy free radicals. So this is the summary of the autoxidation mechanism. So we started off with unsaturated fatty acid. When it is initiate in the presence of enzyme or metal ion, it will form alkyl radical, and this alkyl radical will propagate in the presence of oxygen from the surrounding to form lipid peroxy radical, and then it will combine with another unsaturated fatty acid, by the abstraction of hydrogen atom to form peroxide. Now the formation of free radical stabilized by resonance. For example here, the abstraction of hydrogen to form free radical can be from carbon 1 or carbon 3. This is one example, 9-octadecenoic acid. So the formation of a radical can be at carbon 8 or carbon 11. 8 or 11. It's always next to the carbon having double bond. So this will result in two pairs of resonant hybrids. So these are the resonant hybrids. If the abstraction of hydrogen is from carbon 8, then you have two this set here. If the hydrogen abstraction is from carbon 11, then you get this set here. So therefore there are a total of 4 isomeric hydroperoxide. Another example is autooxidation of linoleic acid, systematic name 9,12-octa-deca-dianoic acid. So this will result in the formation of 3 isomeric hydroperoxide. And of all these 3, okay, the conjugated one will occur in the greatest quantity due to its more stable formation. Okay, so this is the 3 resonance. Of all the 3 resonance, the one in the conjugated form is will have highest quantity compared to the other 2. Okay, next we look at the composition of hydroperoxide to alkoxy and hydroxy free radical. Okay, so we have the hydroperoxide here, okay, decomposed into alkoxy and also hydroxy free radical. And this alkoxy radical can react to form aldehyde and also alkyl radical. This aldehyde that is formed can be a short chain volatile compound, or it can be attached to the glyceride part of the molecule. In this case, the compound is non-volatile. The volatile aldehyde are the one responsible for the oxidized flavor of fat, which result in rancidity. So this alkoxy radical can also abstract hydrogen from another molecule to yield alcohol and a new free radical, and this can propagate, okay, through chain reaction until it terminates. Okay, so this shows the alkoxy free radical abstract another hydrogen from another molecule, another fatty acid, which in turn will form alcohol and also a new radical, and this radical will propagate, okay, through chain reaction. So some of the free radical may interact with each other, which in turn will terminate the chain, and once termination occur, it leads to the formation of ketone. Okay, so we have the alkoxy free radical here, okay, meets with another radical, okay, to form ketone. Okay, so once ketone is formed, the propagation terminates. So this table here shows the formation of aldehyde from the breakdown of hydroperoxide from several oxidized fatty acids. Okay, so these are the fatty acids here, and the methylene group involved in the breakdown, and these are the isomer of the hydroperoxide form. Okay, and these are the aldehyde formed from the decomposition of this hydroperoxide here. Okay, this graph shows the peroxide formation and its decomposition as a function of time. So during the induction period where the free radical is initiated, the peroxide value is 0. as it propagate, okay, over time, um, the peroxide value will increase, okay, because it's being formed, okay, during the propagation phase, until at one point it stabilizes um, during the termination phase, okay, where the radical meets with another radical, and then once it terminate, of course the peroxide value will decrease, okay, and this is the decomposition phase. So a combined index of primary and secondary oxidation product will gives a better evaluation of the state of the oxidation of a particular oil, and this is expressed as Totox value. Totox value means total oxidation value. So this is the formula. Totox value is 2 times peroxide value plus anisidine value, okay, so 2 times PV plus AV. So AV is a measure of the secondary oxidation product, in this case aldehyde. So primary, the PV value is mainly from the hydroperoxide. Okay, so the lower the PV, the better the quality of oil, because when the PV is low means the likelihood of formation of aldehyde, okay, AV, would be low also, because this is the one that determine the formation of secondary product, because the PV value will leads to formation of aldehyde, okay, the AV value. So most customer will require PV value less than 10 for marine oil. So the best is PV value is as low as 2. So next is the anisidine value. The AV value is depending on the decomposition of the PV, hydroperoxide. So the hydroperoxide decomposed to form carbonyl and also aldehyde specifically. So this is the one that responsible to the rancidity of oil, okay, undesirable rancid smell. So therefore, the lower the AV value, the better the quality of oil. How to get low AV value? Low PV value. Okay. So most customer will require AV value less than 30 in marine oil, but it need to be as low as 10. So the lower the Totox value, the better the quality of oil. So this green curve shows the Totox value. This purple curve is the PV value, and this red curve is the AV value. So the formula is Totox value is 2 times PV plus AV. So if the PV is high, AV also would increase. So when PV high, AV increase, the Totox value would be high also. Okay, so that's why low Totox value means better quality, because if these two are high, means high aldehyde compound, which leads to rancidity.